Okay, let's start getting going here. Got a lot of stuff to get through today as far as administrative stuff and new material. So today we're going to talk about grades, hopefully for no longer than 15-20 minutes, and then we'll finish up 8.3 and we'll start 8.4. Those are the grades. Now let me do this. Let me pass back. Well, you know what? Let's talk about grades first, and then I'll pass them back, all right? Because once I pass them back, I probably won't have your attention. So what I decided to do is take a look at Exam 1, which is in blue, and Exam 2, which is in red. And I think when I first met everyone here, I'd walked in, handed you back your Exam 1. I had shown you this distribution of Exam 1. I said there were a lot of Fs, and that, do you remember me talking about the bell curve? Trying to get this class more towards like a bell curve. If you just take the blue out of here and just look at the red, it looks pretty much like a bell curve. You have a couple of A's, which are above average, exceptional grades, I guess. And then what you want is the same thing on the other end. You don't want a bunch of people to be on the low end, right? You want few A's, few F's, more B's, D's, and then in the middle, your average. So this is actually a good distribution for the red. What I thought was really interesting was this. This is every student in the class. In the order that I put them in is the blue. I know it's hard to see, but the blue is Exam 1, and this is students listed from lowest to highest for Exam 1. So this particular student got a 41 on Exam 1, and then 43 for the next student, and the blue goes up, right? So the highest grade on Exam 1 was a 105. I thought this was really, really interesting, because look what happened. The students on the low end of Exam 1, almost all of them came up. Do y'all see that? Almost all of them came up. Like every one of these blues, it's up. In fact, the highest grade in the class on this test came from a student who did not pass the first test, which was really interesting. In fact, I want to talk to that student. If they get their test back and they want to talk to me, I'm interested to know what happened between Exam 1 and 2. And then towards the middle, some weird things happened. Like right in here, right in the group of students that were right around D's on the first exam, most of them dropped on this exam, which was weird. And then a lot of the students that were in the C range, right, went up a little bit. The B's went up a little bit. Now, I did have some interesting situations where I had a student who made a C on the first exam and then a low score on the second exam. And then, this one right here, an 85 on the first one, a 50 on this one. So those, again, would be students I'd be interested to know, like, what happened between, the first exam and the second exam. Make sense? Yes? So I'm trying to like pay attention to you specifically, but I can't call you out and be like, okay, what happened? You have to want to engage me a little bit and talk to me about your grades. If you look at this, there's another way to look at it. I guess not. This is the same thing, but the other way. So I'm listing out Exam 2 from lowest to highest, and then the blue is what they got on Exam 1. But you get the same information here. So interesting. The class average on this test was a 75. Yeah, on the first exam, the class average was a 69 with a 16-point standard deviation, meaning that the scores ranged, 69 plus 16, take away 16, somewhere in there. This exam average, the standard deviation was about the same, a little smaller, which is good, but the class average was higher, 74.3 on this test. Okay? Any questions on that? Okay, so this Friday is the last day to drop a class. So most students want to know like where they stand in the class. What I'm going to do is I'm going to call your name. I want you to come up and get your exam. When you get your exam, on bottom of the second page will be a number that's in a box. That's your grade right now on this test. All right, so this is what it'll say, something like, I'm just making this up. It'll say minus 13, like that, and then it'll say like 78, all right? I don't even know if that's right, but what this means is that there were 12 problems on the test. I counted each one were 10 points. So this student missed 13 out of the 120 points, which means that you got a 78, right? So you don't subtract 13 from 100 and say that's your score, all right? It's 13 taken away from 120, then divided by 120, and that's your percentage. All right, so that's just the grade on this test. Then I'm also going to hand you a slip of paper, all right? It's going to have some numbers on it, all right? And here's what it is. I'll put it up here. Yeah. It's going to give you 4 numbers. Well, it's the best marker I have. Would you mind throwing me, do you mind throwing me one of those, the black one there? Yeah, toss it. Okay. Not much better. All right. So it's going to have your name. It's going to have 4 numbers. All right. Now I'm going to make up these numbers. All right. It's maybe 103 here. Then I'll say something like 81, and then something like 62, and then, I don't know, 78. All right. So let me explain what these numbers are. Everyone wants to know, like, can I pass the class, right? I mean, that's, well, not everyone. I mean, some people are like, I don't know if I should drop. Should I or not? So it'll have your name, and then this first number is what you would need to average the rest of the class. In other words, we're going to have quizzes. We're going to have another exam. We're going to have a final. If you take those and average them together, right, you need that to average out to be 103 for an A in the class. Which means what for that student? Probably not going to happen, right? I mean, unless there's some bonuses involved. Man, there are no good markers in here. Y'all understand what I'm saying or not? Okay. And then the next number is what you would need to get a B in the class. Now keep in mind, if it's saying If it's saying 81 in order to get a B, that means you could get a 75 on exam 3. But that means your final needs to be better, right? It needs to average it out to be an 81. 62 would be what they need to pass. So for the people who are interested in what you need to pass, can I pass the class? You're interested in that number right there. That'll get you a C, that'll get you through the class. Then this right here, the last number, is actually your grade right now in the class with quizzes factored in, with bonuses factored in, just where you stand right now in the class, okay? The problem is on Canvas, the way Canvas computes the grade, it's not an accurate grade. It's hard to explain. I don't want to get into it. But it doesn't know that you've only taken a few quizzes, not all the quizzes for the class. So it's treating your average for quizzes right now as if you've done them all, which is not true. So it hasn't weighted the grade properly, and therefore it's not an accurate grade. All right? That's one thing I don't like about the Canvas grades. Any questions on that? No? Okay, so this is going to take a little while because I've got to, one at a time here. Joel Ramirez. If you get your test back and you have any questions on what I did, like as far as how I graded, if I took off points and you're like, why do you take off points? Please just come talk to me about that. I know there are a few students that I took off for no work. So like it was just like a graph and there was no like work where I could see where you found your 5 points, things like that. I'm willing to discuss that with you and maybe reward you some points, but you have to justify that answer. All right? Robert Tuck. These are coming back to you in no particular order at all. They're probably in the same order you turned them in. De La Vega. Is De La Vega here? Yes? Ben? I believe also that every student who took exam 1 took exam 2. I think. I had a grade for everyone. We may have had 1 or 2 drop. Ernesto Rios. Right here. And from that, I created the test. So if you go back and you look at, like, find all 6 trig functions, I don't want to go through this whole thing, but if you look through your notes, somewhere in the first lecture, here we go, like, find all 6 trig functions. Oh, wait, that's an angle. Where did we do the right triangles? Probably in the beginning. Well, you'll have to just believe me. If you go through the lectures, you'll see that there's a problem like every single problem on the test. or it came from the review problems. All right, so I hope that you feel that it was a fair test. You know, I do remember telling you, make sure you study your review and your notes. And so what do you all think? I don't know if you can talk candidly, if you feel comfortable enough to be honest about it. I can take criticism. I'm here to try and help you learn, so do we want to try anything different? I mean, are we still okay with me being up here like this with the video? Do we want to go to a board? How do y'all feel? Let me just feedback. Anyone? Okay. Okay. Anyone else feel the other way? Would prefer me to be on a board? Don't be shy. Okay, so I think that some of you are probably pleased with the results here. I know that there's probably others that aren't. But overall, I'm happy with an average of a 75-ish. I'm happy with, less people with Fs. But we have to move forward, and the class is going to get much more challenging. It's going to get much more challenging very quickly. So this next section, 8.3, we've already started, so we kind of have seen it. But 8.4 is where the pre-cal really starts to take on its own life, and you'll see it's going to require a lot of practice, which is why your homework assignments are going to be huge for these. For 8.3 it's going to be pretty big, but 8.4 it's going to be a lot of problems, like 30 or 40 problems. It's a lot. But that's the only way to get good at it. That's really the only way. I mean, you can watch me do them and go, oh, I got it. But trust me, you can't do these unless you've done them yourself. Yes? They can be. It depends on if you get stuck. If you get stuck, as you'll see today, I mean, one thing you have to always remember as a student of math, it's one thing to sit there and watch me do it and go, yeah, because I'm not getting caught in those places that students get caught in because I've done so much of it, right? I don't get hung up. So you're seeing the unflawed version of the problem being worked out. It's very different than when you're sitting at home doing it. So the only way to get good is to practice. Practice. Okay, so let's get started with 8.3. And I want to, if I can, see where we left off here. I was just doing examples. I don't think I was numbering them anymore, was I? Let's say that was 8.3.6. Let's say we're going to make this 8.3.7. If you'd like to talk to me about your test after outside of class, please come by. Especially those of you who got taken off for no work. I know that sometimes it upsets you, but you can justify your answers to me. All right, so if you recall, 8.3, this section was about solving trigonometric equations. We want to be able to solve equations involving trig functions. And there were a few like that on your test, right? Number 11, I think number 10 also. It was 10. 11 was, and yeah, 10. So number 10 and 11 were both solving trig equations. They're pretty basic ones. But what I was trying to get us to see when we were doing this, that I wanted you to be able to do two things here. I wanted you to be able to solve this equation and give me the general answers, and then solve the equation and give me specific answers on a given interval. And that's the same thing I'm going to ask for here. So this is an equation, right, because we have an equal sign. It's a trig equation because we have a trigonometric function involved in the equation. What do we call the thing inside the trig function? The argument, okay? We have the argument of the trig function, which is kind of weird. We have not had this yet. We've had things like theta, we've had 2 theta, we've had 3 theta, but we haven't had theta plus a number, which is what we have here. But the way we go about it is exactly the same. We're going to try and isolate the trig function, okay, get it by itself on one side of the equation. So I will take that -1, I'll move it to the other side by adding 1 on both sides. And that will give me tangent theta plus pi over 4 equals 1, right? So what I'm saying to myself now is, am I familiar enough with tangent to realize that there is some angle, okay, that I could plug in here. There's something that I could plug in, the whole thing, that when I take tangent of it, I get 1. And so you have to be familiar with the unit circle enough to remember that there are 2 places where tangent is 1. And where are those 2 places? Remember, tangent is defined to be the y-coordinate divided by the x-coordinate, right? That's what the tangent is. So to get a 1 to come out, you need to know where the y and the x-coordinate are exactly the same, right? That way you divide them and you get 1. So where are the y and x coordinates identical? First and third quadrant, what angles are they? 45 degrees. So 45 here, and then directly across from that, over here at what, 225 degrees? Those are the 2 places it happens. Remember the whole all students take calculus. Those give you the quadrants where the trig functions are positive. So tangent is positive over here, but it's not positive here. So that's why it couldn't be, right? That's why it couldn't be there, because 1 is positive. And then down here, but not here. So these are the only 2 solutions. But remember, we want all of them, right? So how can I get all of these? And let's stick with radians, not degrees here. The angle here is what? Pi over 4. And then to get around to the other one, I can add a pi, which gives me a half rotation to get to the other one, and just keep doing that, right? Have we done that enough that y'all are okay with that? So I need the argument, okay? I need the argument to be any of those angles. I saw this on the test. There was some confusion here. This argument, theta plus pi over 4, must be equal to that pi over 4 over there plus pi k. So the pi over 4 plus pi k came from this picture. The theta plus pi over 4 comes from the argument. I think on the test what I was seeing some students doing, especially on number, what was it, 11? 11 had 3 theta inside. And so what people were doing is they were saying, here they were putting theta, right? And then they were doing their answer. They weren't doing the pi k. They were dividing this by 3 and not dividing that by 3. So I saw different things, but just keep in mind that whatever your argument is, that's the thing that has to be set equal to your general solution. And then you go about trying to isolate theta. So now let's get theta by itself. So what would I do? How do I get that theta here by itself? Subtract pi over 4 on both sides. And what would happen? Luckily for us, Those pi over 4s cancel completely, don't they? And we get that theta must be just pi k. This is my general solution. Now, what if I asked you to solve this just on the interval 0 to pi? You would just start plugging in values of k, right? So if I now say solve the same equation on the interval 0 less than or equal to theta less than or just less than 2 pi, then you start plugging in values of k. So if k is 0, what do we have? Theta is what? If k is 0, theta is 0. If k is 1, what do we have? Theta is pi. And if k is 2, what do we have? 2 pi. So should I include 2 pi or not? Well, I said here theta must be bigger than or equal to 0, but less than, strictly less than 2 pi. So I can't be 2 pi. So you would throw out that solution there at the end. So your only two solutions would be 0 and pi. All right. Any questions? Okay, up to this point, every trig equation I've given you, it's always worked out where we can go to the unit circle and figure out where we are, right? As far as the angle is concerned. Like this one, we knew we were at pi over 4 and 5 pi over 4. And everything I did in the last class and on the test was something like that. But what if we're presented with a problem like this? 838. And you might want to make a note somewhere around here that this is the first time we're going to solve a trig equation, and it's going to require our calculator to do it. All right, so we're going to do a pretty simple one to start, and then I'll do one more. It's a little more complicated in a second. What if I tell you that tangent theta must be 4? And I want you to give me all the solutions, and then after that I'll ask you for some solutions on an interval. So just give me the general solution of this. Well, do you feel comfortable with the idea that there's not an angle that you know of on the unit circle that's going to give you this? What were the things for tangent that would pop out that we did know? Like if tangent was 1, right, we know what that came from. What were some of the other things that could pop up? Root 3, right? Or 1 over root 3, or 0. Those are really the only ones. Some combination of those were the only things that would work. So this one, not so much. So the only way to figure out, can you all open the door, please? The only way to really figure out what theta is going to work is by utilizing our calculator. I know I brought it. Let's make sure. Where is it? Let's go ahead and get your calculator out, and let's get in radian mode. All right, there it is. Everybody get into radian mode on their calculator. All right, so what I'd like for you to do is look at this equation, come in on both sides of the equation with the arctangent. Now, just some language here. I am not multiplying both sides by arctangent, all right? That's not what I'm doing. I am taking arctangent of both sides. All right, so I'm doing that operation on both sides. What should happen on the left side? When you take the inverse tangent of theta, what should happen? Y'all okay? On the left side, what happens when you put an inverse trig function with its trig function? They cancel each other out, right? So all that would be left on the left side is what? Theta. That's why I did it, right? I did it so I could release the theta from the tangent. So I have now released the theta from the tangent by doing that on both sides. But on the right side, I need to figure out what arctangent of 4 is. And in we said radian mode, right? I would like for you to go ahead and do the arctangent, which you have that key on your calculator, of 4. You should get 1.325817664, something like that. We'll just go about 2-3 decimal places. I'm not too concerned about it. I'm going to go 1.33. If you said 326 or something, that'd be fine. So I know that the angle, theta, is about 1.33 radians. So my question to you now is, where is that on the unit circle? What quadrant are we in? So let's talk about this unit circle again. Remembering that this is an angle, right? If we had been in degree mode on our calculator, you might want to try this if you'd like, do arctangent of 4 in degree mode, and it'll give you the answer in degrees. But you need to be able to work with both, which is why I'm showing it to you in radians. So let me try and determine what quadrant I'm in here. At this angle right here, when I'm here, that's the angle 0, right? When I'm straight up and down, it's pi over 2. When I'm here, it's pi. When I'm here, it's 3 pi over 2, right? When I say pi over 2, I mean pi over 2 radians. But what is pi over 2? So you have to get on your calculator and do pi, which is about 3.14, and divide it by 2. Some of you have a pi key, so you could just use your pi key and divide it by 2. And you should get like 1.57. So this is the same as 1.57 radians. And then at pi is about 3.14 radians. And then do 3 times pi and divide that by 2. And you get 4.71 radians. And then all the way around was 2 pi, wasn't it? And if you do 2 times pi, you should get 6.28, approximately. So what I've done is I've converted the radians, and instead of using pi in the answer, I've just converted it to a decimal, just to a number. And that's good because our answer is just a decimal, 1.38, or 1.33. So what quadrant are we in? We're in the first quadrant, right? Because this is 1.57 straight up, so 1.33 is smaller, so we're somewhere in the first quadrant. I don't know exactly where. I don't really care, to tell you the truth. I just know that I'm in the first quadrant. Now, why is this important? Well, because we know that for tangent, right? For tangent, if our answer is 4, then our angle had to be in the first quadrant, or it could have been in the third quadrant, right? And so I need, by drawing the picture, what I'm doing is allowing myself to realize that the other solution is down here directly across from it. You see that? So we actually have 2 spots on the unit circle where we could get a tangent of the angle to be 4. It's this one plus, and this one, right? Y'all okay with that? Now, is anyone sitting there going, well, wait a minute, hold on. You came in here with arctangent, and didn't you tell us that when we do the inverse tangent, you have to cut off the domain? Remember that? I said that, right? Well, here's the problem. The original problem has nothing to do with arctangent. The only reason we used arctangent was to try and get one of the angles. Once we had one of them, we said, okay, well, look, the arctangent was only there as a tool for us to find the angle. We are not restricting anything. The original problem did not have arctangent in it, right? We introduced that restriction. So we need to remove the restriction and look back over here. Does that make sense? Okay, so how am I going to say my answer? My argument, which was theta, right? Theta was my argument, has to be equal to the 1.33 radians. But then how do I get to this one? I add pi k, right? That would move me around again. Here, add pi k. Just keep making rotations, half rotations. So I add pi k. Now, if you don't like the way that looks, just remember that this is really, what, pi is about 3.14? Okay? You like it that way? All I'm doing is replacing pi with 3.14. And this would be my general solution. Are there questions on that? Sure. All right, well, if there are no questions, I would like for you to now solve that same equation. Tangent theta is 4 on the interval 0 theta less than 2 pi. So now let's let k be 0, and we get what for theta? 1.33. Is 1.33 inside of 0, 2 pi? Yes, it is, right? Because remember, 2 pi is how much? 6.28. This number is between 0 and 6.28. Now let k be 1. If k is 1, theta is 1.33 plus 3.14, which is approximately what? 4.47. And is that inside of this interval? Yes, right? So we have 2 answers so far. How about k is 2? Theta 7.61? Too big, right? That's too big. So our only 2 answers are theta is 1.33 and theta is 4.47. Now, do you believe we got the answers? Let's see. Let's just check it real quick. Let's see if this solves the equation. We're saying if I replace theta with 1.33 and I plug it into this, I should get 4. So make sure you're in radian mode and just do tangent of 1.33. I bet you don't get 4. What do you get? 4.07, something like that? Why is it wrong? We rounded, okay? That's why it's wrong. Now, it's not incorrect. I mean, that's the answer I would take. But we have to understand that there's rounding error in that. Is that a big deal? It depends on what you're doing, right? Like if I'm building a cabinet, right? Let's say a bookshelf, and I'm measuring the width of the boards, is it okay to be off by 7/100ths of an inch? Probably if it's just a bookshelf. If I'm building an aircraft bearing that's going to be inside of an engine spinning around, can I be off by 7/100ths of an inch? No, right? So how far we want to go, how much error we want, is all dictated by the situation you're in. So if I wanted to get a more precise answer, when I did my arctangent, remember I said it was about 1.33, I would have gone further with what the calculator told me. But in this class, we'll be happy 2 decimal places with everything. I'm okay with that. We good? Now just check the other one, see if the other one works. Do tangent of 4.47 and 4.044. So we're still off a little bit, but it's pretty close to 4, right? All right, let's move on. I'm going to give you another example. 8.39. I would like us to solve cosecant of 4 theta plus 1 minus 3 equals 2. All right, so you look at this. It is a trigonometric equation, right? You have an equal sign in here. We have a trig function. It's a cosecant, right? Okay. See how we're going to deal with this. Well, the first thing you ever want to do with the trig equation is to isolate the trig equation, all right? Get that by itself. So I can do that pretty easily by moving this 3 over and just adding it and getting a 5. So I've got cosecant 4 theta plus 1 must equal 5. Now what? Cosecant, we need cosecant of something, right? Our argument, cosecant of something has to be 5. Well, cosecant is not something we've messed with a lot. So I don't think you're going to be able to look at this and just tell me like what the angle is. In fact, no one will be able to go off the unit circle. There's no angle on there. It's going to give you a cosecant of 5. So let me try and help you get to it, all right? First thing I'm going to do is I'm going to rewrite the equation. Let me see if you agree with this. Do you agree that this is true? That's the same thing? That's the definition of cosecant, right? Now what I'm going to do is I'm going to multiply both sides of the equation by that sine of 4 theta plus 1. Now why do you think I'm doing that? I'm going to get it out of the denominator this way, right? On the left side, it's going to cancel, and I'm just going to have what over there? 1. And then on the right side, my sine's on the right side now, right? Now I still have a trig equation, but now it's sine instead of cosecant, which I'm happy about. Why am I happy about that? Because my calculator has an inverse sine function on it. It doesn't have an inverse cosecant function. So I want to be able to use my calculator, but I need to get in terms of sine or cosine or tangent because that's the only 3 keys I have. But I don't have the sine by itself yet, right? What do I have sitting there in front of it? The 5, right? So divide by 5, right? Not subtract because it's multiplication. So if I divide both sides by 5, I get 1 divided by 5 equals sine of 4 theta plus 1. And what I'll do next is I'm going to rewrite the equation the other way, just because we're used to seeing the trig function on the left side and the number on the right side. That's just my choice to write it this way. And so this is where you would go and say, oh, do I know of an angle where I take sine and I get 1/5? So that means the sine function is the y coordinate. Do you know where the y coordinate is 1/5? No. You know where it's 1/2 though, right? Root 3 over 2, 0 and 1, but you don't know this one. So because of that, you're going to come in with your calculator and you're going to do the arc sine on both sides. So I'm going to do arc sine on the left, or the sine inverse, however you want to look at it. Whatever I do the left side, I must do the right side, so I'm taking the arc sine of the 1/5. So introducing that. Now I've created restrictions, but I'm going to take those restrictions away once I draw it on my circle. So tell me what happens on the left side, and just notice my use of parentheses. I'm taking the arc sine of, so here's my parentheses, of what? The entire thing. So when I put the arc sine and the sine together, what will happen? Cancels out, so what's still on the left side? 4 theta plus 1. The whole argument is there. Okay, our entire argument will still be there. So we have 4 theta plus 1 must be equal to, and on the right side, well, get your calculator out. What's arc sine of 1/5? And are you in degree mode or radian mode? Let's stick with radians, okay? If you're in radian mode, what do you get? 0.20, is that good enough for you? 0.2? 0.201? I'll go 201 this time, just to show you if you go 3 decimal places, our answer will be a little closer. That fair? So, now what? Subtract 1, divide by 4. Now, this is what got some people into trouble on the test. See, I need this argument. I need this argument when it's all said and done to turn out to this, right? This is the point where you go to your circle. You do not solve for theta yet. This is like us saying theta is equal to 1/2. Or theta is equal to 30 degrees or something like that. And we go to our unit circle and draw it. And then realize that there might be another answer. And we have to do that before we solve for theta. So tell me on your unit circle, where this is going to happen. Where will you get 0.21? I mean, where is 0.21 as an angle? This is an angle, right? This is an angle. It's in radians. What quadrant are we in? That's all I want to know. What quadrant? 0.2 is in the first quadrant, isn't it? So I'm going to draw this angle. It's really, really small, too. 0.2, it's like way over here, right? Are you okay with that? What is the trig function that we're working with here? Back up here. Sine, right? We wanted to know when sine of something was 1/5. We are telling ourselves that happens when this argument is 0.201. But where else could we get the sine function to be the same? Which quadrant? This is the tricky part. The second quadrant, right? Look, over here, do y'all see this one? Shit. Do y'all see this one right here? Do you agree that that angle, the sine would be the same? Because sine is the y-coordinate, isn't it? So the height of this point, how high it is off the ground here, is the same as the height of it over here. So the sine of those two angles must be the same. Are y'all getting that? That's a critical point here. And what's even more critical is that we're looking at it before we solved for theta. We have to get this general answer first before we come in with this and divide all this out. Okay, so what is that angle? This is the tricky part. We know, well, it's all tricky, I guess. This, we know the angle is 0.201, right? 0.201. That's that angle right there. So my question to you is, what is the angle that starts here and gets you all the way over here to there? 168.4. How'd you get that? Okay. Okay, but are you in radians or in degrees? Okay. So let's stick with radians. You're correct, but we won't even need the inverse though. Let's just think about it as a measurement. If I'm telling you that this measurement here is 0.2, what is it all the way to the other side? What's that measurement? That's pi, right? All the way to the other side is pi. So we want to take that pi, which is 3.14, and we want to subtract from it how much? 0.201. That's how much that angle would be. This angle would be your pi, but take away the 0.201. But pi is about 3.14. Take away 0.201, and what do you have? $2.939? See, there's a lot of geometry happening here. With the arctangent that we did in the last problem, our angle was directly across in the other quadrant, right? And it was pretty easy because we just add pi k. This one is not. These are two completely different angles. Can you jump from one angle to the other the way we did with the arctangent in the last problem? Can you just keep adding like pi k? You cannot do it, right? They are not directly across from each other. So you're going to have two general solutions here instead of one. What are they going to be? What are my two solution sets going to be? First, I need the 4 theta plus 1 to be equal to what? 0.201, right? That's this one. How can I get back here? Plus 2 pi k. This solution set, it's starting out at that 0.201. It's adding a full rotation, or any number of full rotations, will give me all of those points right there on the right side in the first quadrant. Then if I write 4 theta plus 1 equals, what was the other angle? 2.939, but then again, adding any number of full rotations to that will be my other solution. You see how quickly this got confusing? All right, now at this point, you may start to solve for theta. Now you can. So the first thing I will do is I will subtract 1. I'm going to work with this first equation here. I'm going to subtract 1 from both sides. So when I subtract 1 here, I subtract 1 from the 0.201. I do not subtract 1 from this because this has a variable on it, k. So it's just like if this were to say like, 2 plus x, and you subtract 1, you're subtracting 1 from the 2, not the x. So what is 0.201 minus 1? Negative 0.799 plus 2 pi k. Can I change the 2 pi to 6.28 k? Everyone okay with that? Changing 2 pi to approximately 6.28? What do I still have to do? Divide everything by 4. And now, when I say everything, I mean both terms. This can be divided by 4, and that can be divided by 4. So theta must be negative, well, I'll do it on my calculator. I'm doing negative 0.799 divided by 4. I'm getting negative 0.199 plus, now I do 6.28 divided by 4. I'm getting 1.57 k. That's one of my general solutions. The other side, you do the same thing. Subtract 1 on both sides. You get 4 theta. This one's a little easier to do. 1.939 plus 2 pi k, which I'll make it 6.28 k. I divide everything by 4. Theta must be 0.484 plus 1.57 k. Those are my general solutions. It's a lot more work than it looked like it might be in the beginning, huh? All right, questions? Now, what if I asked you the same problem, but I said only the answers between 0 and 2 pi? So I'm just going to try and squeeze it in here. If I say solutions just in the interval 0 less than or equal to theta less than 2 pi. Then I'd start by letting k be 0. If k is 0, what does our first one give us? Negative 0.199. Is that going to work? Negative 0.199? No, theta has to be bigger than 0. So k equals 0 will not work for this one. Will k equals 0 work for the other one? You all follow that? So theta will have to be negative 0.199. No, I cannot have that. But on the other one, I'm plugging in k into this one, 0, I get 0.44. Is that okay? Or 0.484? Yes, that's fine. And now I let k be 1 and do it again. If k is 1, you're going to take 1.57 and basically subtract 0.199 and get theta is 1.371. That's from the first one. And then over there, let k be 1. I get 2.054. Anyone else get that? Yeah? Okay. And are both of those within 0, 2 pi? Yes, because remember 2 pi is what? 6.8. We got a ways to go, don't we? Because these can get bigger, but we're going to have lots of solutions here. So k equals 2 will work. K equals 3. I'm going to skip because I want to move on to the next problem. Let's say k equals 3. I'm skipping k equals 2. So now I'm going to do 3 times 1.57 plus, or minus, I should say, 0.199, which should give me 4.511. And then I'm doing 3 on that one. I get 5.194. I'm still inside, right? That's still good. So I'd have to go to k equals 4. I'm not going to show them all, but when we're going to have like probably, 6, maybe 7 solutions in this thing. And I think what I'll do, just to make myself feel better about things, I'm going to take one of these answers, 5.194. I'm going to check it, just to see if I've got it or not. 5.194. I'm going to try and plug it right in here. So I'm going to go cosecant of 4 times 5.194 plus 1, and then I'm going to take away 3. So 4 times 5.194 is 20.776. I'm going to add 1 to that. So this is really cosecant of 21.776, and then I'm going to take away 3 from that. How do I do cosecant on my calculator? I can do 1 over sine, right? So on my calculator, I'm going to do 1 divided by sine of 21.776. That gives me what? Man, we have so much rounding error. This is pathetic. I'm getting 4.684, then take away 3. What's that? 1.684. Wow, that's way off. But that's how much rounding error. What are we supposed to get? We're supposed to get 2. That's how much rounding error we have in this. That's the danger of rounding, is that if you round too much, you get these you get so much error, it's almost not practical to do it that way. So what's most important to me is when I'm looking at this work, when I give you a problem like this, is for you to actually show the method. Okay, the method is the most important part of it. You being able to identify the angle. You round where you want. I'll follow you through the work. Round where you like, but make sure you're doing everything properly. Yes, I would accept this. Okay, let's move on. 8.3.10. Couple of types of trig equations that we didn't really get a chance to look at. Yes. No, you don't need to. All right, take a look at this equation here. We've had one like this before, similar, but not exactly like this. And what I mean is we have a squared trig function, right? Sine theta squared. Remember that means you take sine theta and then you square it. That's what that actually means. We just like to write the squared right here next to the theta instead of having to write the parentheses. That's just the notation we use. And if you look at this, I want you to kind of realize that this kind of looks like this. You have to squint your eyes. But it kind of looks like this. Doesn't it? Like if I were to say that sine theta is like a u, then it appears here and here, right? So this would be like 2u squared minus 3u plus 1 equals 0. And what type of equation is this? Quadratic. And how do you solve quadratic equations? Well, you either factor them, or you use completing the square, or you use some AC method, or you use quadratic formula, right? Something. So help me factor this real quick over here. Now this is going to all be up to you, how comfortable you are with factoring. To factor something like this, I could use like a guess and check method where I need the first term to be a 2u squared, so I put like 2u here and a u here. I know when I multiply those, I get 2u squared. I need my last term to be a 1, so I could put like a 1 here and a 1 here. But I need my middle term to be negative 3, which means that this needs to be negative, right? And the last term is positive, so I could mess around with this and get maybe that to work. Would that give it to me? So if I now take each of those and set those each equal to 0, I would get u is a half and u is 1, right? So everything I just did here on the side is Math 1414, college algebra, factoring, and quadratic. And the expectation is that you can do that. But over here, we didn't have u, right? We had sine. So I want to show you how I'm going to work this exact same problem, the same way I worked this one, but I'm not going to replace the sine with u. I'm actually going to leave the sign there the whole time. So I'm realizing that this is what we call a trigonometric equation in quadratic form, meaning it's not exactly quadratic, but it looks quadratic in the sense that we have like an ax squared plus bx plus c equals 0. So I know it's going to factor. I'm going to try and get a 2 sine squared theta to start. So I'm going to put a 2 sine theta here and a sine theta here. When I multiply those two together, I get the 2 sine squared theta. I need a 1 in the back and a 1 in the back to give me the 1 back here. I need negative 3, so I put negatives in the middle, and that should give me the same thing, right? You could check it by foiling that would give you this. Now you set each one of these to 0. 2 separate equations now. Now do you see that you have taken your quadratic trig equation and you've turned it into 2 trig equations? Yes? The first one when you move things around, you get sine theta is 1/2. The second one, you get sine theta is 1. And at this point, I say dot, 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 meaning I'm not going any further, but you would have to, right? Now what you would do is you say, oh, where is sine 1/2? You go to your unit circle. You're saying, where is sine 1/2? Oh, it's going to happen at, what, 30 degrees and 150, right? And then you get all your general solutions from that. Over here, where is sine equal to 1? Pi over 2, and then you got to get all of them to come around. Yes? Dot, 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 you do the rest. Not right now, but we don't have time to go through all that work now. The whole idea here is how do you handle this now? You realize it's quadratic, you break it down, and now you've got two things we can handle. All right, one more, and we're going to move into the next section. 8.3.11. How would you solve 3 cosine theta plus 3 equals 2 sine squared theta? It's a trig equation because it has trigonometric functions in it. Do you see that we have the sine squared? So when you see sine squared, you may be thinking, just like the last problem, oh, it's going to be like a quadratic. Yes, I agree. However, this is sine squared and this is cosine. So you got sines mixed with cosines. So what we'd like to do is get rid of the sine and make it a cosine, or get rid of the cosine and make it a sine. You can't just make cosine sine, though. You can make a sine squared something, though, right? Because we all remember, it's all burned into our brains, right? This most powerful trigonometric identity, the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. And if we solve that for sine squared theta, we get 1 minus cosine squared theta, which tells us that I can replace this sine squared theta with 1 minus cosine squared theta. And then my whole equation will have nothing but cosines in it. Some of them will be squared, but it will have cosines only, which is good. So my new equation becomes 3 cosine theta plus 3 equals, be careful here, 2 times 1 minus cosine squared theta. I had to put that 1 minus cosine squared theta in parentheses because the 2 that was in front of the sine squared must distribute through. If this sine squared theta becomes 2 terms, the 2 is going to act on both of them. And now I'll distribute through. That will release the parentheses there. And then what do you think I should do at this point? Move everything to one side because it's quadratic, right? So what I'm going to do is I'm going to add the 2 cosine squared theta to both sides. I'm going to subtract 2 on both sides. And that will give me my new equation, which will read 2 cosine squared theta plus 3 cosine theta. What number is still there? Plus 1 must equal the right side, which is 0. And now, do you see that that's a quadratic? It's a quadratic equation in theta, in cosine theta, meaning I can split this into 2 different factors. I need my first one to be a 2 cosine squared theta, so I'm going to put 2 cosine theta here, cosine theta here. What should I put at the ends of these? I need it to turn out to be a 1, right? So 1 and 1. And then I need my middle term to be a positive 3. So I believe a plus and a plus will work here. Again, this step to this step, this is all on Okay, I don't mean that in a mean way. I'm just being honest. This is a quadratic, and I expect that you can factor a quadratic. Whatever the method is, you need to be comfortable with it. If you're not, just go get some review on factoring. All right, go to the tutoring lab. Say, I need some help. Help me factor some trinomials. Trust me, they get it all the time in there. It's one of the big Achilles heels of math students is factoring trinomials. All right, so now I set each one of those equal to 0, right? I set 2 cosine theta plus 1 equal to 0. I set cosine theta plus 1 equal to 0. This one gives me cosine theta is -1/2. Notice that these are all working out to be things that you know on the unit circle, aren't they? Cosine theta is -1/2. That means where's the x-coordinate -1/2? 2 places that happens. Then you need to get the general solutions. Cosine theta is -1. That happens over at pi, and then you need all the general solutions. So dot, 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 dot. You could take that the rest of the way. Well, this one will give you 2. You have to determine are they straight across from each other or not. They could be. They're not, but I mean, you would have to look at that. And then this one will be, this will just be one general solution because there's only one spot that happens. But you'd need to take that and investigate that yourself. All right, that ends Chapter 8, Section 3. I don't have the page. I don't know why I didn't put the page for that section here, but for 8.3, just go look in the back of that section for the homework. You should look at 11. I had initially put 33 odds, and then I thought to myself, these are students, most of them, who want to take calculus. Not all of you, but these are students who need to get through this course and the next course. So you need to know what the level of expectation is as far as the amount of work you should be doing. I don't think that's realistic. I think that to be real with yourself, you need to actually do 11 through 79 odd. If you can do 11 through 79 odd, which is going to take you hours to do, at least getting to the point where, you know where I said dot, dot, dot? If you can get to dot, dot, dot on those, if you feel comfortable like you can do the rest, at least get to that point on all those. And then, so that you're practicing the factoring and things like that. But if you do that, not only will you be better off for it, better served for it as far as the experience of the different types of equations you can see, but you'll understand the time requirements and the amount of work required if you're going to move into calculus. Because calculus is not a spectator sport for sure. You can't go to class, do an hour of homework a week, and be cool with the class. It's just not going to work. So you should be prepared to do several hours of work. I'm not trying to be mean. I'm just trying to be honest, okay? I don't want you to have some cruel reality walking into calculus, some unrealistic expectation. All right, 8.4, trig identities. Now, in my humble opinion, this is probably the point in pre-cal that students really do not enjoy. And you'll see why. But don't be discouraged by that. Just realize that there's a challenge in this, and if you get frustrated and confused, it's normal. You have to push through it, though. You can't have a problem in front of you and then just say, I can't do it, I'm just going to give up. The good news is that what we're doing is we're given identities, things that are true, and we're asked to show they're true, which means we have to just manipulate them properly. So there is a right answer. There is a way to get to it. It's just, are you going to throw in the white towel before that happens? So before we get into the actual identities, I want to show you some identities, some things we have not seen. They are on your formula sheet. You're free to use these all the time. These are called the even and odd identities. 8.4.1. All right, so I think I'll motivate this with a picture. I'd like for us to go back to not the unit circle, but just an arbitrary Cartesian plane where we take some angle here. I'm not going to tell you what the angle is. I'm just going to tell you it's theta. And that I define some point out here, xy, and then there's some radius, some r, that gets you from the origin out to that point. Does everybody remember what sine of theta is if it's defined this way? Look on your cheat sheet. It's in the top right-hand corner or top left-hand corner of your cheat sheet. Sine of theta is what? Y over r. What's cosine of theta? X over r. What is tangent of theta? Y over x. That's the way we define the trigonometric functions of any angle. And then we went to the unit circle because it was so damn convenient. But we want to investigate, I want to investigate something specific here. I would like us to look at the angle, not theta, but negative theta. What quadrant would negative theta be in? Fourth quadrant. It would be like this. Do you agree that would be negative theta right there? What does this point down here have in common with that point up there? What's the same? The x-coordinates are the same, right? What's the difference, though? The y-coordinate. If this was a positive y, right? If that's positive because it's up in the first quadrant, this y would have to be what? Negative y? Do you all agree? Now, tell me what sine of negative theta is. So that means go to the angle, negative theta. Tell me what sine is. It's this thing divided by r, right? R would be the same for both of these? Sorry, I should label that. R would be the same. So sine of negative theta would be negative y over r. Do y'all buy that? What would cosine theta be? Sorry, cosine negative theta would be x over r, right? And what would tangent of negative theta be? Negative y over x. Okay, so I just did the same three trig functions for that point because I was looking at negative theta instead of theta. Everyone cool with this? Okay, I would like for us to compare something. I would like for you to compare the sine of theta to sine of negative theta. What's the difference between sine of theta and sine of negative theta? What's the only difference? They're off by a sign, right? They're off by a sign. The first one is y over r. The other one is what? Negative y over r. So the only difference between sine of theta and sine of negative theta is a sign. Agreed? Which is the first identity that we have. It's called the odd identity for sine. It says this, and this is what's on your formula sheet. Does anyone have it with them, right in front of them? No? 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 Let's see. I just want to see where I'm referring to here. Here, keep it. Oh, it's the bottom left. It's the bottom left says even odd identities down here, all right? So what does it say there on your sheet? Sine of negative u is equal to negative sine u. Thank you. Do you see where this identity comes from now? It's saying basically sine of negative theta is basically the same as sine of theta, except you change the sign, right? That's the identity. Now, the way that we can look at it is instead of an identity, is saying that if we ever have sine and we have a negative inside, we can take the negative away and just put the negative on the outside. We are allowed to do that anytime we wish. Or if we have a negative on the outside of a sign, we can essentially look at it as pushing it in and changing it. Does that make sense? How about cosine? What is the relationship between cosine of theta and cosine of negative theta? They are exactly the same, aren't they? They're exactly the same. Which is why on your formula sheet it says what? Cosine of negative u is equal to cosine of u. That identity says that if you have a negative inside of a cosine, it can just go away. Just goes away. Or if you have a positive in there, you can turn it into a negative. It doesn't change what's happening. And then what does it say for tangent? Well, let's investigate tangent. How are tangent of theta and tangent of negative theta related? Just like the sine, right? They're off by a sign. So this would be tangent u, negative u, is equal to negative tangent of u. Are those the only three on the sheet? There's what? Cosecant? So cosecant matches with sine. Why? Because cosecant is the reciprocal of this. Secant is going to match with cosine. And then cotangent is going to match with tangent. I'm not going to put those up there, but these are the even and odd identities. Now, why do they call them even and odd? That's beyond the scope of this class. It's something that that is much easier to explain in Calculus 2. But if you've ever heard of like functions being symmetric, you can graph these, and the symmetry tells you if they're odd or even. But even then, you don't know why they use odd and even, like why they use those two words. So Cal 2, you ever take Cal 2? I promise you take it with me. I'll show you why it's even and odd, why they call it even and odd. This right here, these two are called odd functions, and the cosine is an even function. But all you need to know is those identities. Now, let's begin with the fun stuff with identities, all right? Those are the only two. Just remember that on your sheet, the Pythagorean identities, remember those? And then also all the identities that we started with, like tangent is sine theta over cosine theta, right? Cotangent is cosine theta over sine theta. Secant is 1 over cosine. All those identities are fair game right now. And what we're going to do is we're going to try and look at some things and simplify them. So 842. 842. I would like for us to simplify cotangent theta over cosecant theta. I'd like for us to simplify that. And you might say, hey, that looks pretty simple to me. I don't think there's anything really I need to do with that. But that actually cleans up to be something a lot nicer. So when you're looking at this, just start using some of the identities that you know, like the basic identities. What is cotangent of theta by its definition? 1 over tangent. And how about in terms of sine and cosine? What is it? It's sine over cosine is tangent. It's cosine over sine. So this is cosine theta over sine theta. Everyone agree that that is what cotangent is? And then divide that whole thing by, and notice my division bar is longer than the one above it, because I'm separating this cotangent from this bottom. And what is cosecant? 1 over sine, right? So this is 1 over sine theta. How important is that division bar being longer than these two? It's actually pretty critical. I know a lot of students won't realize it when they're doing math that it's important, but let me just illustrate it with something. What if I ask you this? What am I asking you to do there? Divide 4 by 2 and then divide that by 3? Or am I saying divide 2 by 3 and then divide that into 4? Or does it matter? Does it give you the same answer? Let's see. If I did this first, I would get what on top? 2, and then 2 divided by 3 would be like 0.666 forever, right? Yes? But what if I did it the other way around? How about if I had done the 2 divided by 3 forever first, or 2 divided by 3? What would that be? 0.6666. So I would get 4 divided by 0.666 forever. And that is definitely what? Bigger than 4 divided by this should be bigger than 4. I mean, 4 divided by 1 is going to be 4, so 4 divided by a smaller number should be bigger than 4. That's 4, so which one's correct? Which one's right? Bigger than 4, sorry. Do you see it? It matters, right? So I actually cannot tell you what the correct answer is because you didn't draw it properly. You had to tell me where the major division was happening. So I would have had to have drawn it like 4. If I go 4 divided by 2 divided by 3, then I know the 2 divided by 3 goes first, and then you divide that into 4. So that's the same thing here, a little subtle little FYI. Okay, so what do we do with this? Whenever we have a fraction divided by a fraction, you can always flip. Essentially, this is what you're doing. You're multiplying sine theta over 1, sine theta over 1 like this. On the bottom, what happens? Goes away, it turns into a 1. And on the top, what happens when you multiply? The signs cancel, and all you get is cosine theta. So cotangent theta divided by cosecant theta is equivalent to cosine theta. They're the same thing. Now, I would like for you to look at that. What were the instructions there for that problem? Simplify, right? I gave you something and asked you to make it look nicer. We made it look nicer. Compare that to what I'm about to do here. Show this is true. I would like for you to show me that if you take cosine theta, divide it by 1 plus sine theta, that's the same as 1 minus sine theta divided by cosine theta. And if you haven't taken pre-cal, let me introduce you to your first identity problem, all right? This is your first real show me this is true problem. Show that this is an identity. Show that regardless of theta, these two hold true. I mean, there are some issues but with division by 0, but if it messes this one up, it messes this one up. So just show me that this is true. So the question becomes, how do we show that something is equivalent in mathematics? And this is very, very important that you don't screw this up. You've been taught your whole life that if you have an equation, you can do the same thing to both sides, right? Yes? But see, we actually don't have this equation. We are being asked to show that this is true. You are not allowed to multiply both sides by anything here. You must start with one side and massage it, change it, do something to it, and make it look like the right side. Or you can start with the right side and massage it into the left side. But you cannot work with them both at the same time. That is the way you show something is true. Understand the difference? So what I'm going to do is I'm going to pick a side. And normally we start with the side that looks more complicated. Here, it's kind of hard to say which one's more complicated, other than to say that the left side has 2 terms in the denominator, which is a little more complicated than something on the right that only has 1 term in the denominator. And if you're ever in doubt of which side to start with, you just pick one and see what happens. If you get stuck, then go back, start the problem over, and go with the other side. There's going to be trial and error here. There's going to be a lot of problems, issues. This is left-hand side, LHS. I'm letting you, the reader, know that I'm going to start with the left-hand side, and at the very end, hopefully I'll be able to write RHS because I'll have the right-hand side there at the end. We'll see if I can get there. So writing my left-hand side down, the equation, I would like to turn it into the right-hand side. I can do anything I want to this as long as it is a true, valid algebraic move. Understand? It's kind of like, anyone here play chess? Anyone ever played chess? Anybody know what the pieces do, right? Like you can't take up, a bishop doesn't act like a queen. I mean, like you can't, there are moves that are legal in algebra, there are moves that are not legal. As long as you do legal moves, then you're on a path. As soon as you break a rule of algebra, it's over. And there's no real hint here as to how to get to it. So you ready? There's going to be a lot of me showing you things, and you going, oh, wow, I would have never thought of that. But now you know that that's something you could do. So here, let me give you my thought here, and it's quite a bit of thought, and then I'll write it down. I realize that I need to turn a 1 plus sine theta. Somehow it's got to turn into a cosine theta on the bottom, right? So I'm thinking, how do I get sines to become cosines? Well, I have the Pythagorean identity, right? Sine squared theta plus cosine squared theta equals 1. That allows me to switch cosines and sines. Didn't we just do it a little while ago? Yeah? But I can't just make this thing squared. I cannot just square this. Is that a legal move? If I have something sitting there, if I square it, is it the same thing? If I have the number 3 sitting there and I square it, is it still 3? No. Now, if I have an equation, I can square both sides. That's fine. But this isn't an equation. This is just an expression. So I'm not allowed to just square top and bottom. So that would be nice. I wish we could do that. We can't. So how am I going to get this to turn into somehow sine squared without squaring top and bottom? Well, and what does that Pythagorean identity give us again? Where was that thing? Remember this right here? Right? We said I can move things over, right? I could say sine squared theta is 1 minus cosine squared theta. I could have moved the sine squared theta over, and it would have read cosine squared theta is 1 minus sine squared theta, right? Either way. So with all that in mind, just tell me if you believe that I can do this. Can I multiply this by 1? Yes, okay. Can I make my 1 this? Can I? Yes? Now, why in the world would I do that? What have I foreseen is going to happen when I multiply that denominator out? This is a difference of 2 squares, isn't it? This is a difference of 2 squares. It's 1 plus sine theta, 1 minus sine theta. So when I do that, I'm going to get 1 times 1, which is 1. I'm multiplying straight across the bottom. And when I do 1 times negative sine theta, I get negative sine theta. Sine theta times 1, I get positive sine theta. Those middle terms cancel. What's my last term going to be? Negative sine squared theta. And right there, right now, do you see why I did this? Because what's 1 minus sine squared theta? Cosine squared theta, right? Now, what's still on the top? I still have to multiply the top, don't I? So I'm going to multiply cosine theta times this, right? But hold on, don't do it yet. Just leave it there for a second. Don't do the multiplication. Why am I not going to do the multiplication? Because look at where I'm trying to get to. Look at what I'm trying to get to. Do you see that I have a 1 minus sine theta there? Do you see I've got it right here? Now I have a cosine here that's not here. I have a cosine on the bottom, but wait a minute. We said this was going to turn into what? Cosine squared theta? So this is cosine theta times 1 minus sine theta over cosine squared theta. And what happens with those cosines? I can cancel one of them from the top and one of them from the bottom, which leaves me with 1 minus sine theta over cosine theta. And that is the right-hand side. And so I'm done, right? I've taken the left-hand side. I've done nothing but correct algebra to turn it into the right-hand side. So as you might expect, there are many different approaches you could have taken to this, and there are many approaches that would have gotten you lost. And that's where I was saying you could get kind of frustrated with this. All right? One more before we run out of time. For this one, the instructions are to simplify. Um, 1 plus sine u over sine u plus cotangent u minus cosine u over cosine u. Am I asking you to verify an identity here? No. I'm just asking you to take that thing that's pretty ugly and make it look better. And then we get into a gray area because it's like, what's better? Some people are like, hey, I'm cool with that. That's simple, you know? No, we mean like do some work here. Make it maybe, where now we have two fractions, right? Maybe just make it one fraction, right? That actually just gave you a hint of a way you could try and simplify it. How about getting a common denominator? Could you get a common denominator between two fractions and put them together? Sure, but you'd have to introduce things, right? What would our common denominator need to be? Sine u, cosine u, right? So what's this one missing over here? Cosine u. So I have to multiply by 1 on just this fraction, cosine u on top, cosine u on the bottom. And then on the other fraction, what do I need to introduce? Sine u, right? Just on this one, just on that one, that should give me a common denominator. And I will have to multiply this cosine u times these two only, the sine u times these two only because there's addition between these. So let me go ahead and distribute this. This cosine u is going to distribute here and here. And then this sine u will distribute here and here. When I distribute all that out, all of that will be over the common denominator, won't it? So all of this is over, let me see, our common, so let me distribute this. Cosine u times 1 is cosine u. What's cosine u times sine u? I don't know. It's cosine u times sine u. That's what it is, all right? Can't do anything to that. Cosine u times sine u is cosine u times sine u. Sine u times cotangent u. Oh, notice there's a plus here, right? That's the separation here, plus. Now this, sine u cotangent u. And then sine u times negative cosine u would be negative sine u cosine u. Am I done up top? If I multiplied everything out on top? Yes? So this is all divided by the common denominator. Does it matter if I write cosine u sine u or sine u cosine u? Like, does this order matter? It's multiplication, right? Multiplication doesn't matter, so I can write it either way. Does anybody see anything good? Yes, that is going to simplify. Before I do that, is there anything else up here? Cosine u sine u being added, and then subtracting sine u cosine u. But I just said these are the same thing, aren't they? So these two completely wipe each other out, which is great. And then it was just pointed out that if you look at what sine of u and cosine of u is, and maybe you just look at that on the side here. Sine u times, I said cosine, cotangent u. What's cotangent? It's cosine u over sine u. Do y'all see that? Sine u cotangent u is sine u times cosine u over sine u. And that first sine u is really like a sine of u over 1, isn't it? So what can you do here? You can cancel the sine u. These cancel each other out. And all that leaves you with is what? Cosine u. So this thing that I circled is just really a cosine u. It's just kind of hidden, but that's all it is. So here's where I am. I have a cosine u up here. We said that this right here just turned into cosine u again. So how many cosine u's do I have? 2 of them, right? Not cosine squared because I'm adding them. So it's 2 cosine u's over sine u, cosine u. And again, because this is multiplication down here, and this is multiplication up here, I am allowed to cancel things. So these cosines now cancel, right? And all I'm left with is what? 2 over sine u. That's the same as 2 times 1 over sine u. So all I'm doing here is I'm pulling the 2 out in front because I realize that 1 over sine u is what? What's 1 over sine? Cosecant. So this is 2 cosecant u. It's like a big puzzle, all right? It's like a big puzzle, and you just have to try and put everything together. Yes? Mm-hmm. Well, because we added them, it's 2 of them as opposed to cosine squared u. If it was cosine squared u, then you would cancel 1, you'd be left with the cosine, and you would cancel that one out. You see the difference? Look, cosine squared u over cosine u is not the same as 2 cosine u over cosine u. Because this one on the left is cosine u times cosine u over cosine u. This one over here is cosine u plus cosine u over cosine u. So here you can cancel one out, and you're just left with cosine u. Here the most you could do is break it up into 2 fractions, because we have 2 terms on top, 1 on the bottom. So you say cosine u over cosine u plus cosine u over cosine u. But what's cosine u over cosine u? 1 plus 1, which is 2, which is the same thing you would have got had you just canceled them to begin with. You see the difference? Okay. Those are the little subtle pieces of algebra that are going to slowly start to really get solidified in your mind. When you have to do this stuff, you can't make algebraic mistakes, so you really start to learn it. All right, we are out of time. I had another 3 pages of examples to give you, but I'll tell you what the homework for this section is going to be, and if you'd like, you can start. You might get stuck. I recommend you possibly look through the examples that are done in the book, okay? That's actually what I'm doing right now. I'm doing the examples in the book because, you know, looking at the way they're done in the book and then watching someone do it are 2 different things. But if you want to try and get moving ahead, that's what I'm going to come in and do on Monday, is the rest of the examples in that section. So 638, I'm going to ask you to do 19 through 63 odds. That is not, I'm not saying you need to complete that assignment by next class. But if you complete the other assignment, get started on this, that'd be a good thing. Yes. Everybody have a good weekend. All right. I don't need to take attendance because I know who wasn't here. Who didn't pick up their test? Anyone not pick up their test? Okay. Have a good weekend.